Now, let's go look at problem-solving strategies. It is difficult to actually try to go through step by step because each circuit is so unique. So this is sort of like a rule of thumb of what to do. So the first thing you want to think about is that before the switch is thrown, so we're talking about t equal to 0 minus, assume the storage elements have reached their initial steady state values. Then replace them with their equivalents. So in this case, we could imagine that we have a capacitor and so when I'm looking at this capacitor, we know for a fact that it's going to have some initial steady state value. And we could then replace it with its equivalent. In other words, it behaves like an open. So it retains this voltage, but we know for a fact that the current here is 0. And our other situation is that we have our inductor. And in the inductor situation, we then have that we have a current running because it's saturated at 0 minus. Because it's a constant current, we then treat it as a short. So we know that it has a current IL of 0 minus, but its voltage is now a short, which is 0. So what we do then is that now use simple circuits to determine x of 0 minus. So now we're at step 2. Storage elements always control the behavior of the circuit since they are time dependent. Sources aren't time dependent. While there are some, resistors and everything else are not time dependent. So after the switch is thrown, focus on using simple circuits, which is, so when I say that, which is usually a combination of KCL and KVL to isolate dx of 0 plus slash dt. Assume there are discontinuities with these variables. However, this is not necessarily the case every single time. So to give you a sense of what I want to do next is that I want to go after an example just to give you what we should expect. So in this example here, we want to determine all initial conditions. So that means I need VC of 0 plus, IL of 0 plus, dV of 0 plus dt, and DIL of 0 plus slash dt. So let's pick a nice circuit, and let's assume that our circuit here is going to look something like this. So I'm going to have a voltage source, which is 12 volts. Then I'm going to have some resistors and capacitors and inductors. And then you'll see here that I have a switch here that's going to close. So this is a 2 microfarad. This is a 6K, a 6K, and this is a 3K. And this is going to be 1 millihenry. And so the switch here closes at t equal to 0. So now we start the process. So I'm going to start with step 1. At step 1, we are at t equal to 0 minus. So it's in a, that implies that we have the initial steady state. So if I have the initial steady state, then I have to replace all of these guys with their equivalents. So I'm going to copy this and bring it down. Whoa, I don't know what happened. Let me try that again. And then I'll just modify it. There we go. So when I'm looking at this thing, this switch is open, so this is gone. So this is my circuit right here. The capacitor now is an open. The inductor is a short. So if I come in here and just modify this a little bit nicer, we're seeing that I have an open, and this is plus or minus VC of 0 minus, and I have an inductor current going in this way that's also in its initial steady state. Now, this is a fairly straightforward circuit to solve, right? So we're going to say we're going to use simple circuits to calculate VC of 0 minus and IL of 0 minus. So if I look at, you could see that the voltage of the capacitor is the same as the 6K on the right. Then I'm going to find, actually, you could calculate it multiple ways. So let's say, so I'm going to use VDR to calculate VC of 0 minus. So if I do that, that tells me here is that VC of 0 minus is then going to be the same as the voltage across this. So VDR says then I'm just doing the outside loop, really. So then this becomes 6 plus 6 into 6 times 12 volts. This tells me that this is plus 6 volts, which then tells me that the voltage of the capacitor before and after the switch is 6 volts. Now that I know since the current of the inductor is the same that's going through the 6K resistor, I could just apply Ohm's law. So I'm going to use Ohm's law to calculate IL of 0 minus. So then I see here is that the inductor current is the same as the current of the 6K because they're all in series. So since we just calculated the voltage of the 6K, I could write V6K at 0 minus divided by 6K will then be 1 milliamp. So then that tells me here that the current of the inductor after the switch is thrown must remain at 1 milliamp. On a further note, because this is the initial steady state, there is no current through the inductor. I mean, through the, right? So if I look at this current here, IC of 0 minus is of course 0. And the voltage across here, because it's of a short, the voltage of the inductor at 0 minus must also be equal to 0. So we know then that IC of 0 minus is equal to 0, and VL of 0 minus is also equal to 0. So now we move on to step 2. So when I move on to step 2, I'm going to come in here and I'm going to copy this circuit again just to be faster. And what we're seeing here is that we're looking at t equal to 0 plus 1 focuses on calculating the voltage, the time derivative of the voltage of the inductor, and the time derivative of the current of the capacitor. And we said before, assume that there are discontinuities. So here I go. So the switch now is closed. I'm going to come here. Oops. So the switch now is closed. And I'm going to take these guys out because we don't care about the value of the inductor and capacitor right now. So what do we know? We know that the voltage of the capacitor must be the same. So in other words, so when I look at this guy, it has to remain 6 volts. But we assume that there's now a current through the capacitor at 0 plus, because you can have a discontinuity. And at the same time, we're saying here that we assume here that the inductor continues to have the same current. However, the voltage of the inductor is assumed to change. So our goal here is to find the voltage of the inductor and the current through the capacitor. Now, as a heads up here, you can see here that I have a 6 parallel to 3, so this is really a 2K. I won't redraw the circuit with the 2K. We're just going to assume that we have 2 loops. So there are 2 loops in the circuit. So now, let's go and draw this out. So I want to determine VL of 0 plus. By the way, I could have determined the current of the capacitor. Just, I don't know, I'm just picking V, voltage of the inductor. There's no order here. So now focus on the right loop. Now remember, the right loop contains the capacitor, the inductor, and the 2K resistor. So if I draw this out, what am I seeing? I see here that I have my capacitor, I have my inductor, and then I have my 2K resistor. So what do I know? I know that this guy must be 6 volts. It cannot change. So our focus here is to calculate what is the voltage at 0 plus. That immediately tells us that we have to use KVL, but there's a condition here, and the condition is that IL of 0 plus has to remain for an instant at 1 milliamp. So if this resistor here is a 2K resistor, we can see here that this is the voltage of a 2K resistor. By inspection, you can see here that the current running through the 2K is a 1 milliamp. So this immediately gives us that the voltage of the 2K is 2 volts. So let's write that down very briefly here, that since the current cannot change the voltage of the 2K must be, according to Ohm's law, we see here is that the 2K at 0 plus is then going to be 2K times 1 milli, so I'm going to get 2 volts. As a consequence, we now apply KVL to calculate VL of 0 plus. And when we do that, I can isolate VL of 0 plus, which will then be the voltage of the capacitor minus the voltage of the 2K at 0 plus. So then this will give me a voltage of 6 minus 2, which will then be 4 volts. And this will be the voltage of the inductor. So when I look at this, what am I seeing here? There's a discontinuity jump. So as expected, the inductor's voltage instantly changed. So in other words, when we look at the inductor voltage, what happened? It came in and it started off at VL of 0 minus was 0. And then what did it do? It jumped up to a point. It started at 0 here, and then it jumped up to a value of VL of 0 plus equal to 4 volts. So if I'm looking at VL as a function of time, you're seeing something like this. And as usual, as you go towards the final steady state, we're going to see that this guy's going to disintegrate all the way down to 0. But we won't talk about that nature of the curve. It could be more complicated than that. So we have to look at the cases where that happens. But that's not our initial condition. This is not one of the initial conditions. This must be written into DIL of 0 plus dt. So when I look at this, using the inductor equation. So if I look at the inductor equation, it now reads this, that it's DIL at 0 plus dt is going to be 1 over the inductance times the voltage of the inductor at that point. So this is 1 millihenry And this is 4 volts, so that turns out to be 4,000 amps per second is what we're seeing here. That is the initial condition right there. Now we're left with determining IC. So now let's go determine IC of 0 plus. So what we want to do is that we want to focus on the VC node and the left loop. So let's isolate the left loop and focus on the VC node. So let's draw this out again. So I have my voltage source here, and we already agreed that this was 12 volts. Then I have my 6K resistor. And then here's my VC node. And then I have my capacitor here. So if I'm going to focus on this node right here, I have to also worry about the inductor current here. So what do we know? We know that this guy must be 6 volts. But at the same time, we expect a current of the inductor to now change as it's moving. On the other hand, we're seeing here that we have a current here where this must remain at the switch of 1 milliamp. Let's write this a little bit bigger. So now that I have this, we could immediately, looking at KVL, we could calculate what the voltage of the 6 ohm resistor, because you could see it's got to be 12 minus 6 to give me a 6 for the 6K resistor has to be 6. So applying KVL to calculate V6K at 0 plus, that tells me here that that has to be VC of 0 plus is then going to be 12 minus 6, so it's going to be 6 volts. So using Ohm's law, the current I6K at 0 plus must be the voltage of this guy at 0 plus divided by 6K, which gives me 1 milliamp. Now apply KCL at node at the VC node. So if you're looking at the node here, you're seeing that we have what? We have a current that's going through here that's 1 milliamp. And then I have an inductor of 1 milliamp that tells me immediately that the current through the capacitor must be 0. So again, drawing this out, we have the 6K resistor, we have the capacitor here, and then we have the inductor. So I know that I have 1 milliamp coming this way. I know that I have 1 milliamp coming this way. So the only conclusion we have here is that IC of 0 plus must be 0. So in this case, the capacitor's current does not have a discontinuity. So if I look at this thing, we're seeing that we have a current where this is something like this here. So this is IC of T. We see that the current of the capacitor here is 0. And then we see that after the switch, immediately, that's also 0. But that's not the initial condition. The initial condition is that VC of 0 plus dt must be 0 as well.